Hello guys, so welcome back to my channel, and today we're gonna do something about integral equations. So this is actually going to be an introduction to integral equations. And wait, you've been watching my videos, you haven't subscribed to my channel. What are you waiting for? Subscribe. Alright? Alright, so let's get it. Integral equations. We all know what basically differential equation is. For differential equation, you know that you definitely have an unknown function, and this unknown function is what you're looking for. Say, so let's say du dt is given as say u, right? So before you can solve this, you have to separate the variables, and you're gonna have something like du on u equals to dt. And after doing your integration, you realize that you have ln of u equals t plus t. All right. So in the actual sense, you're going to have something like u being equal to c e to the power t. This is the solution to the differential equation. So you have an unknown function which you're looking for, right? Yeah, this is the unknown function you're looking for. So and you can actually see that the unknown function was found in a derivative, right? Yeah, so in the same way, if I want to define what an integral equation is, I should have an unknown function, all right? But here, the unknown function is supposed to be under an integral sign, okay? So for instance, since you are going to be using a general integral equation, let me give that the general integral equation over here. We can have something like u of x being equal to a function of x plus the integral from a b to b of of xt and y of t dt. So here we actually see that, oh sorry, it's supposed to be u, not y, please, I'm sorry. So u of t dt. So you can actually see that the unknown function u, which you are looking for, is also found under the integral sign. Okay, so the unknown function u we are looking for is found under the integral sign, which makes this whole equation an integral equation. And we are going to talk about this kind of integral equation so much in over here. All right, so today we are going to actually describe this kind of integral equation, the parameters in it. So let me put a lambda over here, and we're going to talk about that, the lambda too. So we are going to know the elements of this integral equation. Then we're going to learn some scenarios where this can become homogeneous. This can become a first kind integral equation or a second kind integral equation. It could be a Volterra integral equation or a Fredholm's integral equation. So let's go straight at it. So here we have some terms over here. We have, first of all, I'm going to talk about my f of x, and this term, we call that the free term. And you have lambda being an investigative parameter. K of xe is the kernel of the integral equation. So this investigative parameter is actually an eigenvalue of this kernel. All right, and we are going to talk about the kernel too. And I think, yeah, so these are the three basic things, or the three basic elements you're supposed to know. And you know that your a of x and your b of x are your limits of integration. Okay, yeah. So free term is actually just a function of the independent variable which stands alone in this equation. So it's a free term. It's a function though, but it is a known function, and you this isn't what you're looking for. You're looking for u of x. So even though this is a function of x, it isn't what you're looking for. It is known function, so we call that a free term. All right. Then when you come here, you have this one being a parameter, which is an investigative parameter, which is that way. And with the kernel of xt, like the kernel, which is k of xt, it is the primary part of this whole integral equation. This is what we really need to solve our integral equation. Okay, so this kernel it's a very interesting term we are going to talk about in this topic. Okay, yeah, so the kernel is what it is. Yeah, so let's talk of some scenarios over here. Scenarios. So scenarios. Let's say scenarios. First of all, this free term can be 0. So like I said, it is always known. So this can be 0 or non-zero. Okay. So if the free term is equal to 0, okay, we have a homogeneous integral equation, and vice versa. Okay, so if this free term is 0, you have a homogeneous integral equation, and if this free term is non-zero, you have a non-homogeneous differential integral equation. All right, yeah. So now let's go to the limits of integration. If the limits of integration, are constants, then we have a Fredholm's IE. Yeah, so having these to be constants, you have a Fredholm's integral equation, and we have a Volterra IE otherwise. Okay, so we are basically saying that if these two are just constants, then you have a Fredholm's integral equation. But on the other hand, if both of them are functions of x, or one of them is a function of x, then you have a Volterra integral equation. But we are actually going to see or talk about a specific type of Volterra integral equation where you have your upper limits rather being a function of x and the lower limits being a constant. Okay, yeah, so that's what we will be talking about when we go to, or when we get to Volterra integral equations. Okay, yeah, so now I think we have these two scenarios. Then when we realize that the function of interest, the unknown function you're looking for, is under the integral sign here, okay, and it is also outside the integral sign. Okay, so if you have the unknown function occurring under the integral sign, that is what we are looking for. But if you also have it occurring outside the integral sign, then you have an integral equation of the second kind. Okay, that's the integral equation of the second kind. So let me say, if u of x equals 0, we have an IE of the second kind. Oh, wait. If it is equal to 0, then it is of the first kind, because we expect that the function is supposed to be under the integral sign only. So this is going to be of the first kind. Okay, and we have the second kind, i.e. if u of x is not equal to 0, which means that if, so what this basically means is that if you see that the function you have to look for occurs only under the integral sign, you have an integral equation of the first kind. Okay, but if you have the unknown function to be looked for outside the integral sign as well, then you have an integral equation of the second kind. Okay, yes. So this is another scenario, and I think the last scenario we're going to talk about is comparing, just talking about the limits and the function under the integral sign as well. So we have a singular integral equation and we have a non-singular integral equation. So an IE, an integral equation, is singular if, okay, so here an IE, the singularity of an integral equation is going to depend on the integration itself. Okay, you don't consider all these things. You don't consider lambda, you don't consider the free term, you don't consider this term too. You're only considering this integral. Okay, and what you are actually talking about here is that if the limits, or let me say, if the integral is improper. Okay, so if this integral is improper, you actually have a singular integral equation. So when does an integral becomes improper? If any of the limits is infinity. Okay, if any of the limits is infinity, you have an improper integral equation, or you have an improper integral. Okay, and once you have an improper integral over here, the whole integral equation becomes singular. Okay, or you can have this known kernel here. You know, this kernel is actually known in the square AB in the dimension of x. X ranges from a to b, and you have t2 ranging from a to b. So if you are going to have the xt plane and draw the square, the kernel is always going to be in that square. Okay, so this kernel is always known. All right, so if this kernel is discontinuous at some point, which means at some point in time you have an infinite value here, it makes it also undefined, or it makes it improper because there is a point of discontinuity within this range. Okay, so if that also happens, then it means that you have an improper integral over here, making the whole integral equation a singular one. Okay, yes. So these are the basic scenarios we have to put in mind. So in our next video, we are going to actually talk about the solution of an integral equation, where we are going to have examples of integral equations. Then we try to realize that, or we try to find out whether the solution suggested actually fits the integral equation. So please, if you haven't subscribed to my channel, please subscribe and turn on post notifications. All right, see you in the next video.